Thank you so much for hosting me. And I have a lot of material. So the title indicates that I could talk about 2 papers, but given that time is restricted, we have to choose at some point which particular subjects we're going to cover. So what I will do in the beginning is to give a broad overview, and maybe I'll touch on some subjects that not everyone is familiar with, but then after about 10 slides, I will start introducing everything from scratch. So I will just give a broad overview and then start from scratch, okay? And the work is co-authored with a very talented graduate student, Jiaqi Huang, who is a third-year student by now at Penn State. All right. There are 2 papers on the approximation of minimax regret rules, and then there's a paper about pilot data. And the pilot project is still work in progress and builds on the first paper. So I'll refer to the first paper as GH25. All right. Okay, for the pilot project, so we're looking at a Waldian framework of statistical decision theory. So there are 4 key components, right? That we have a set of DGPs for the observable vectors. Then there's an action space for the policymaker, and then there's a loss function and some criteria on how to evaluate treatment rules. Okay. And here we're looking at a Waldian framework for statistical decision theory, where the policymaker actually needs to make 2 decisions. The first decision affects the sampling design. I'll give an example in a second. And then ultimately, the second decision is for the policymaker to choose a treatment for the population. And the objective is to approximate finite sample minimax regret rules, where regret is defined as the shortfall in expected outcome. As I said, I'll define all these concepts in great detail. Shortfall means you're comparing the highest expected outcome that could have been reached by the optimal decision versus the one that you're getting using the treatment rule that you are applying. Okay, so here's a more precise example, factoring in the pilot setup. So we have a policymaker that ultimately needs to choose a treatment, let's say amongst 2 treatments. The setup is such that the policymaker first observes outcomes from a pilot study. So the sample size is N, and N1 observations are for the first treatment, and N2 observations are from the second treatment. Okay, and then after the pilot study has been observed, money becomes available for N prime additional data points. And here's where the policymaker has to make a first decision. She has to decide how to split up the N prime additional observations amongst the 2 treatments. So how many observations together from treatment 1 and how many together from treatment 2. And then action 2 is, upon observing outcomes from both rounds, from the pilot and the follow-up study, which treatment to apply to the population. Okay, so typically, if you're familiar a little bit with that type of literature, typically the setup is just that the policymaker observes data, and upon observing the data has to make a decision which treatments to apply. So here I want to draw attention to the complexity of the setup, which is substantially more complex than the one that I just gave you, because for the first action, a number N1 prime has to be chosen amongst 0 to N prime. Okay, N prime could be 100, so we have to pick a number from a set of 100 possibilities. And then only then, that seemingly much simpler thing has to be decided upon, which treatments to pick from a set of 2 treatments. And then we also have the sequential nature of the setup. So a seemingly much more complicated setup. And questions that we're interested in here in the pilot context, will there be a sizable reduction in minimax regret, given the additional leverage that the policymaker has in influencing, or at least partially influencing, the sampling design, relative to the case where no pilot study was observed and the data is a priori split into 1/2 for treatment 1 and 1/2 for treatment 2. And then even more general, given a fixed sample size, so that would be N plus N prime, okay, the entire sample size, what is the minimax regret minimizing pilot size and split up of the pilot into treatment groups? So given you have an overall sample size, how would you split it up into a pilot and a follow-up study in order to minimize minimax regret? Okay, so how do we tackle that problem? What we show is that we can simply apply, with some modifications, the techniques that we introduced in the first paper in GH 2025. So in GH 2025, we propose a numerical algorithm for approximation of minimax regret rules. Okay, and discuss some simple applications in that paper. In the current project, in the pilot project, we illustrate that the techniques introduced in the first paper are very versatile, that they can be applied also to that seemingly much more complicated problem. So we hope that we provide at least a partial answer to the challenge that Mansky summarizes in the conclusion of a recent Econometrica paper to the application of statistical decision theory to for policymakers to implement policies. So he says that the primary challenge to use of statistical decision theory is computational, and we provide algorithms that, at least in certain setups, tackle these computational challenges. Okay, so what are the key ingredients of that algorithm in 2025? And why actually do we need algorithms? The problem is that analytical solutions are not available. At least they are available only in very narrow contexts. I'll talk about those in the literature review very briefly, but typically we don't have analytical formulas for minimax regret rules. Okay. So the next thing then would be to numerically approximate them, but also that has been out of reach up to now. So here's what we do in the first paper. We start off with a setup where potential outcomes YT, so YT is the outcome when treatment T is applied, are in the unit interval. Okay, so that's the starting point. Then we show that we can actually restrict attention to a much simpler case, namely situations where potential outcomes, are just binary. So you can view them as success or failure. And why can we do that? We can do that because of the so-called coarsening trick. That's not something that we introduced first. It's something that has been known before. Namely, that if you have a minimax regret rule in the binary case, then you can analytically generate a minimax regret rule in that case. Okay, so being able to tackle this case automatically generates an analytical way to treat the first case, with the case where potential outcomes lie in the unit interval. Okay, and to tackle the binary case, we adapt a version of the algorithm in Robinson 1951 that was introduced in games for two people with finite action space and zero sum. So we adapt that framework, or we fit our setup into the Robinson framework by introducing a hypothetical game where the policymaker plays against an adversarial nature. So nature tries to harm the policymaker. That's why it's a zero-sum game. Whatever the policymaker payoff that the policymaker gets is minus the payoff that nature gets. Okay, so it's by construction a zero-sum game. It's a two-person game, right? Policymaker against nature. The only challenge is that in our setup, the game is not automatically finite because the nature picks the DGP for the potential outcomes. Right? That's not a finite action space. That's a very, very large action space. So nature can pick any distribution over YT. Okay. So the first thing we do is to discretize the parameter space. Obviously, by doing so, we are altering the game. But we show that if we discretize fine enough, then we have by a continuity argument, the minimax regret values of the discretized game will converge to the minimax regret value of the original game. So if you pick the discretization fine enough, then by and large, you get the same result. Okay, I'll discuss the details later. So the algorithm, the adapted version of Robinson's algorithm, works as follows. You iteratively calculate best responses to the current strategy of the other player. So there's the current strategy of nature. Then you calculate in the finite action space a best response by the policymaker to the current strategy of nature. You update the policy by the policymaker, and then vice versa. Then nature calculates a best response to the current strategy of the policymaker and updates its strategy. Okay, so that's how it works. So the computational challenge is that you have to calculate those best responses. And importantly, and that makes the whole project feasible, is that we show that actually there exists a closed form solution to the policymaker's optimization problem. So we don't have to use any numerical method when it comes to updating the policymaker's policy. We can derive it in closed form analytically. So the remaining computational hurdle then is simply the maximization problem, finding the best response for nature. Okay, and for that we use grid search. So there's still a computational challenge there, but when T, the number of treatments, is 2 or 3 or even 4, now that we are using Julia and not MATLAB or Gauss anymore, we can handle 4 treatments by now. But at some point it will be binding and you cannot implement that algorithm anymore. Okay, and I won't have time talking about this. I've talked with previously on one-on-one a little bit. I mentioned that we have additional leverage to speed up the computation by exploiting certain symmetries. Okay, but I will not go into details. The idea here is that minimax regret rules are known to occur as Nash equilibria. And we show that if you restrict the treatment rules by certain symmetry conditions, you can still find Nash equilibria in this restricted game. And obviously, once you restricted the treatment rules, you have to search over smaller spaces. So we document that we can speed up the computation quite substantially by exploiting such symmetries, but I will not go into details. Okay, nice features of the algorithm that we propose. In each iteration of the algorithm automatically provides an upper and a lower bound on the actual minimax regret value of the game. And those bounds converge to each other. And the current treatment policy of the policymaker has maximal regret that lies in between those bounds. So you know at every stage of the algorithm by how much the current policy's maximal regret is at most away from the actual minimax regret value. So if you're satisfied with that difference, if you find that the difference is at most 0.001, you can terminate the algorithm. Okay, so at every stage of the algorithm, you get that information. Furthermore, our procedure readily allows for incorporation of a priori knowledge that the policymaker might have on the set of DGPs that nature can use. Oftentimes in applications, if you think about, say, a job training program, you would assume that the mean wage after job training is none smaller than without job training. So oftentimes we have information about such means, and we can then incorporate that into our algorithm directly without any additional challenge. So in the first paper, we look at seemingly very simple examples, but they have not. There's nothing in the literature that successfully tackled those previously. So we take the case where we have 2 treatments, but the policymaker observes unbalanced samples. So N1 is different from N2. When N1 is equal to N2, that's one of the few cases where there's actually an analytical result about the minimax regret rule. But when N1 is different from N2, there's no analytical result. And we first apply our algorithm to that simple case. We also apply it to the case where we test, where the policymaker tests 2 innovations against the status quo. So that example would be where currently a vaccine is being used, say, and the policymaker knows everything about the outcome distribution under that vaccine. And then the policymaker observes data on 2 new vaccines. Okay, and upon observing the data on the 2 new vaccines, she has to decide whether she wants to switch to one of the new ones or stick with the old one. So nothing is known in the literature for that case. There is an analytical result for testing 1 innovation against the status quo, but nothing when you test 2 innovations or T minus 1 innovations. Okay, and recently we also managed to include covariates, which is of key importance, right? The policymaker wants to tailor individually the treatment assignment to individuals based on observed covariates. And this unfortunately makes the computation or the application of the algorithm much more time consuming, because essentially it increases the number of treatments that the policymaker has to choose. So if we have a binary covariate and we have two treatments, then essentially it becomes a four-dimensional optimization for every time that we have to update nature's policy. So we can incorporate a binary covariate, but that's at the moment the limit. And we have already invested quite a bit into our algorithm using Julia now with CUDA and other methods. It would be completely infeasible, I believe, to do it in Gauss or MATLAB, but Julia is so much faster, it's really mind-blowing. So. Okay, so what do we need to do to modify the algorithm that I just defined from the first paper when we applied to the pilot project? So for the pilot project, given that the action of the policymaker is twofold, right, and there is a sequential nature of the actions by the policymaker, we have to do a little bit of work. So first, we have to be very careful in defining the strategy spaces. The strategy by the policymaker is naturally defined as a behavior strategy. Yeah, I don't know if you remember your game theory from back in the day. But what we really need here to get this finite action space to apply our algorithm is the notion of pure strategies and mixing over them. And luckily, there's a theorem by Kuhn, 1953, that shows that the two notions are actually equivalent. So mixing pure strategies and behavior strategies are one-on-one when it comes to the outcome probabilities and expected payoffs. So that's a key ingredient here, Kuhn's theorem. And then we have to show how to calculate best responses. And we derive best responses by the policymaker using backward induction. And trick 3, that was this important step here, that the best responses by the policymakers are given in closed form. So we show that this is also the case for the pilot project, that the calculating best responses for the policymaker is given in closed form. We also have a variant of the coarsening theorem. So again, we can restrict attention to the case of binary outcomes. And the idea of the pilot study could be iterated, where essentially the policymaker influences the sampling design at every step of the way. So the policymaker observes one observation and then can decide whether the next observation is for treatment 1 or treatment 2. So a fully adaptive design, but of course, at some point, the computational hurdle becomes overwhelming. But intuitively or theoretically, we can fully incorporate an adaptive design. All right, so now I'm starting from scratch. All that was just an overview. If now you don't understand something, you should ask, because now I'm really giving all the building blocks. All right, so given what I said about the coarsening trick, we start with a setup where potential outcomes YT are binary. So 0, 1, you can interpret those as successes and failure if you like. And there are two treatments that the policymaker ultimately has to choose from. Okay, then there's the notion of a state of the world, which is simply a joint distribution for the potential outcomes Y1 through YT. In our hypothetical game, this is what nature will choose. Okay, for simplicity, I'm discussing the case without covariates, but I mentioned that we can incorporate a binary covariate at least. And obviously, the decision maker, the policymaker, does not know S, the joint distribution, because otherwise it would be a simple exercise. You would simply pick the treatment that yields the highest expected outcome. So the policymaker does not know S, but she's partially informed about S by observing a sample Wn of size n. And there are various possible sampling designs, but the data always looks like that. So it always has two ingredients, the observations for every individual. First, the policymaker learns which treatment Ti, individual I, was exposed to, and then what the outcome for that treatment was, for that individual was in the sample, YTII. Okay, and the sample size is n. And here are some examples of how that sample could be generated. The example that I will focus on throughout the talk is the fixed treatment assignment, where a priori sample sizes for each treatment are chosen, so N1 and N2 in the case of 2 treatments, and the policymaker observes N1 IID observations for treatment 1 and N2 IID observations for treatment 2. Alternatively, we could have a so-called random assignment, where the sample size is N again, and for each I and T, the probability that individual I was treated with treatment T is equal to PT for certain probabilities PT. Okay, so here you could theoretically end up with a case where all the observations in your sample are for treatment 1. Okay, that could happen. And then I already mentioned the framework of testing and innovation. Here it is assumed that the distribution of YT is known and data is observed for the first T-1 treatments. And those data points could be generated via I or double I. Okay. And then importantly, for given Ti, we assume that YTII is an independent draw from YTI. Okay, that will be important in a second. All right, then formally, what is a treatment rule? So we want to inform the policymaker, we want to suggest an optimal treatment rule to the policymaker. What is a treatment rule? It is simply a mapping from the observed data to a probability distribution on the set 1 through T. So simply telling or simply choosing with what probability you are intending to pick each of the treatments. So we are allowing for randomized treatment rules. So here we have the T-1 dimensional simplex. So it's vectors, T-dimensional vectors with non-negative ingredients that sum up to 1. So it's simply a probability distribution on the set 1 through T, with the understanding that that denotes with what probability the policymaker intends to use each of the treatments. Okay, and we assume in this agenda here that the policymaker cares about expected outcome. So here we index by S, which is the DGP that nature chooses. And here we have the random outcome. Okay, and we introduce that random variable B that resolves the potential randomness in the treatment rule. So the random variable B is such that the probability that B is equal to T is equal to delta TWN. So that's the probability with which the policymaker chooses treatment T. So at some point, when you have a random treatment rule, you have to resolve the randomness and decide which treatment are you actually applying. And this is done through the random variable B. Okay, we assume that the policymaker cares about this object. You could think about other functionals of the outcome distribution. For example, in this paper, we are looking at the alpha quantile instead of expected outcome. And interestingly, in this paper, we actually get analytical results. We derive optimal treatment policies with respect to minimax regret, when instead of expected outcome, we use a quantile, which is highly surprising because you would think that if with expected outcomes, the analytical challenge is overwhelming, then with quantiles, it should be even harder. But it turns out that we can actually show with quantiles, we get sort of a negative result because we can show that any treatment rule is minimax regret optimal when it comes to quantiles. Anyway, so what is the criterion that we are using? In the context of expected outcome, we're focusing on minimax regret. Now, for those of you who don't know what minimax regret is, let me quickly define it. Let's first introduce that notation. Mu t denotes the expectation of yt. Okay? And regret is defined as follows. Regret for a given treatment policy delta and a given joint distribution S is defined as how sorry the policymaker feels that she went with treatment policy delta when in fact she could have chosen something better. So it compares the maximal expected outcome that she could have obtained minus the expected outcome that she's getting by picking delta. Okay, so regret is about this gap between the expected outcomes, the optimal expected outcome and the one that she actually got. And then what is a minimax regret treatment rule? It's simply a solution to this argmin max problem. So we are trying to find a treatment policy delta that minimizes the maximal regret, where the maximum is taken with respect to all possible joint distributions that nature could have chosen. Okay, and here, important insight is that S the joint distribution for y1 up to yt only matters via the mean vector. Okay, why is that the case? Well, sampling by assumption is IID. Okay, so instead of the joint distribution, only the marginal distributions matter. And given that we are in a binary context, the marginal distributions are pinned down by the mean. Okay, so importantly, from now on, when I refer to an S, I'm simply thinking about a t-dimensional mean vector. Okay, and now it becomes also obvious what I mean by discretizing later. The action space by nature is not discrete, but we can simply take a fine grid over this space here. This is what I'm going to do in a second when we discretize the action space by nature. And then when the policymaker has a priori information, then that mean vector lives in a subspace M of this compact set.
I can just quickly ask something about the first formula. So if the strategy delta is such that I go all in on the T, which maximizes the mu, then I will just get 0 all the time, right?
What does mean you go all in on the mu?
The probability I put on the T that maximizes the mu T is just 1, so the P is just 1. All other ones
okay, so you do a deterministic treatment rule, okay?
And then this would always be 0, right?
No, that I mean, so if the maximum here is obtained for T equal to 1, okay, and you pick T equal to 1, then your regret is equal to 0.
Yeah.
But if you pick, if the maximum here is obtained when T is equal to 2, then you would feel sorry, right? Because your regret is mu2 minus mu1.
Yeah, right. So you don't know what to do.
Yeah.
Okay. Yes.
So, and the issue is that picking deterministically 1 is very good when mu1 is maximum, right? But it's not uniformly good over all the GPs that nature takes, right? So therefore, the policymaker wants to be informed by the sample about which of the treatments seem to perform well.
Okay, thank you.
Okay, so there's a rather scarce literature about analytical finite sample minimax regret rules, simply because they are very hard to derive. Important papers here are by Steuer 2009 and 2012. I have a recent paper with a graduate student where we generalized Steuer's result from 2009. That's the case where we have fixed treatment assignment. So with N1 equal, with N1 and N2 observations, and we are generalizing that to T treatments, from 2 treatments to T treatments. However, minimax regret as a criterion has been applied in many recent papers in the empirical welfare maximization literature, but in an asymptotic framework. And I'll do this very quickly here. I don't have much time. Then when it comes to numerical approximations of minimax regret rules, there's a recent paper by the Cornell lab. It's a group of very influential researchers at Cornell that have a grant, I believe, to work on topics of empirical welfare maximization. And they have a very interesting paper where they use convex optimization routines rather than what we are doing, which is called fictitious play, using Robinson's algorithm. And if I have time, I can talk about the pros and cons. So I don't believe that their method is applicable to the kind of problems that I'm studying here. But they have very important other applications. So they look at cases of partial identification. They also apply their algorithm in a recent paper to a seemingly unrelated topic, namely calculating optimal tests with respect to a particular weighting scheme in a situation where the null is composite. So generalizing or looking at the setup of Elliott Müller-Watson in Econometrica 2013 again, and they provide or they apply this convex optimization routine to that setup here as well. So it's friendly competition. If I have time, I can discuss what I perceive are the advantages of our procedure, at least for the given applications that we are looking at. Okay, and then there's also a recent literature on using or in the context of pilot samples. Okay, so I'm doing this very quickly because I don't have much time. All right, so let's talk about the first paper. So I gave the general context, the objective of the object of interest, right? Approximating these minimax regret rules numerically. because they are not given to us in analytical form. All right, so I already mentioned that we are adopting or adapting Robinson's 1951 algorithm, which is applicable in a situation where we have a two-person finite zero-sum game. So we managed to do this by viewing our setup as one where the policymaker plays against an adversarial nature. So payoffs are equal to negative regret. Okay. Payoff for the policymaker is equal to negative regret, and payoff for nature is equal to regret. Okay, so it's summed up to one. So we naturally have a two-person zero-sum game. The only component missing is the finiteness. So how do we get a finite action space? Well, as I already mentioned, the obvious thing, we are simply discretizing nature's action space. So we are looking at the space of mean vectors rather than taking 0, 1 to the t. We use a epsilon discretization. So you pick a small epsilon, and what is an epsilon discretization? It's simply a finite subset of the original mean vector space, and such that for every mu in M, you can find a mu epsilon in M epsilon that is at most epsilon away from you. So typically what we simply use is an evenly spaced grid with step size epsilon. Okay? Okay, but by doing so, you're altering the game. You're making nature less powerful because nature now has fewer vectors to play with, right? So in particular, the minimax regret value, that is the original minimax regret value, is now becoming smaller because the maximum is over a smaller set. So nature becomes less powerful. But you can easily show that at least when R is continuous, the regret function continues in the second slot, that then as the discretization goes to 0, you find that the minimax regret value of the discretized game converges to the one of the original game. And you can also show that if you use a treatment policy that is optimal in the discretized game, in that sense here, if you use such a sequence of treatment rules in the original game, that then as the discretization epsilon goes to 0, the treatment rule will attain the minimax regret value in the original game. Okay. So these are just asymptotic results in the sense that what happens when epsilon goes to 0, what you really want is explicit bounds in a given application. For a given epsilon, what is at most the difference between V and Vm, right? And we have been working on that. We have explicit bounds in certain applications, but it's super tedious. So I don't think we'll have a general result that applies to all the contexts simultaneously. I think it always has to be worked out example specific, and each example is very tedious and time consuming to do it. Okay, so now we have a finite action space for nature, and we automatically have a finite action space for the policymaker by design. Because given that we are in a discrete setup, in a binary setup, all the histories or the samples that the policymaker observes, that's a finite set, right? It's always a string of zeros and one, and there are only finitely many of those. So we already have a finite action space for nature if you simply take non-randomized rules and you allow mixing over them. So, and that's exactly what we do. There's only finitely many non-randomized rules, right? For every history that you observe, you have to decide whether you apply treatment whether you apply treatment 1 or treatment 2, right? That's what non-randomized means. And given that there are only finitely many samples, the space of non-randomized rules is finite. And we allow the policymaker to then mix over those finitely many non-randomized rules. Okay, so the action space for the policymaker is the non-randomized rules. And the policymaker is then allowed to mix over those. Okay, so here's how the algorithm works, the adapted version of Robinson's algorithm. Pick a theta bigger than 0. That denotes your tolerance by how much the policymaker is willing that the maximal regret of the suggested rule differs from the minimax regret value. And then I already mentioned in the introduction that the algorithm requires updating the mixed strategy by the best response that is obtained in each iteration. And for the updating step, we need these updating weights alpha n. I'll talk about those in a second after I get the overall setup of the algorithm. Okay, so we initialize with an arbitrary treatment policy delta 1, one of the actions in the set of non-randomized rules D. And we further initialize nu by setting it equal to 0. Nu will grow into the mixed strategy by nature, and R naught is initialized at 0. R naught is a lower bound on the maximal regret, a lower bound on the minimax regret value. Okay, so with these initializations, let's look at the iteration step of the algorithm. I mentioned that we iteratively calculate best responses. So let's assume that the policymaker is currently using delta n. Okay, that's the treatment policy by the policymaker after iteration n. Now we have to calculate a best response by nature in the finite action space M epsilon to that mixed strategy by the policymaker. So we have to solve this problem here. We have to find a nu that maximizes regret given that the policymaker uses delta n. Okay, and we are introducing notation here by Rn. We are denoting this quantity here. And this is obviously an upper bound to the minimax regret value, right? Because for a given delta, nature is doing the best it can. So it doesn't mean that the policymaker already did the best. So this is clearly an upper bound to the minimax regret value. So if the upper bound to the minimax regret value minus the current lower bound to the minimax regret value is smaller than psi, then the algorithm terminates and you have found a minimax regret rule. Sorry, you have found a rule whose maximal regret is at most psi away from the minimax regret value. Okay, otherwise, if this condition is not met, then you update, then nature updates its mixed strategy by including that best response that was just calculated, updating its current mixed strategy. Okay, so it downweighs slightly the current mixed strategy and includes the best response. Okay, so I of x denotes a point mass of size 1 at the point x. Okay, and now we do exactly the same thing for the policymaker. Given a current mixed strategy by nature, we are solving this minimization problem. So the policymaker picks a best response to the current mixed strategy mu n by nature, and then updates its treatment policy to delta n plus 1. So slightly downweighs what it previously used and includes with weight alpha n plus 1 the best response that was just calculated. Here's an I missing actually, point mass. Okay, so that sounds plausible, right? But what can we say about convergence? So Robinson proved a convergence result for a particular choice of weights, namely when alpha n is equal to 1 over n. There's a more recent paper by Leslie and Collins that allows for a larger class of updating weights. Okay, so what do the weights need to satisfy? What conditions? So assume the sequence alpha n of updating weights is such that they are always non-negative, they converge to 0 and sum up to infinity. So those two conditions reflect the two restrictions that we need on the updating weights, namely that they still sufficiently update the policy. So this is what this condition here implies, but not by too much. Okay, this is what alpha n going to 0 achieves. So if the weights satisfy these properties, then the maximal regret from the sequence of treatment rules, delta n, that is generated from the algorithm, so maximal regret of the sequence of the delta n's, this converges as n goes to infinity to the minimax regret value. So we are not claiming here anything about conversions of the treatment rules themselves. We are simply saying that the maximal regret associated with that sequence of treatment rules converges to the minimax regret value. Under additional conditions, you can also enforce conversions of the treatment rules, but this is really irrelevant to us. We simply want to make sure that we end up with a treatment policy whose maximal regret is close to the minimax regret value. And we experimented a lot in simulations, and we find that those weights here worked very well in terms of conversion speed. Okay, let's talk about computational challenges. So the algorithm requires calculating best responses for nature and for the policymaker in each iteration step. And I already mentioned that we have an analytical result that says that when it comes to calculating an optimal response by the policymaker, we actually don't have to do that numerically. We have an analytical way of doing that. And here I want to illustrate that that is very important. Actually, the whole project would collapse if that was not the case. So think about the fixed treatment assignment where we have two treatments, or the policymaker has two treatments to choose from, and she's informed about the population distribution by N1 and N2 observations for each of the treatments. How many non-randomized rules are there? Actually, there are that many non-randomized rules. 2 to the N plus 1, N1 plus 1 times N2 plus 1. Okay. Because for every possible history, so obviously what is relevant is only the number of successes. So when you have N1 observations, you can observe 0 successes, 1 success, 2 success, up to N2 successes. So you have N1 plus 1 possible number of successes that you can observe in a sample of N1, and likewise for the second treatment. And then you, for non-randomized rules, you either apply treatment 1 or treatment 2. So you have two choices. So that is the number of non-randomized rules. If you take N1 equal to N2 equal to 300, that number here is 10 to the 27,000. That's a pretty big number. If you have to do grid search over that many possibilities, you will never get anywhere, right? So here's the main insight of the paper, and I expose it's completely trivial, but nobody has pointed that out before. So the main insight maybe of the paper, of the first paper, is that the best response by the policymaker can be determined analytically. And the trick is just the trivial observation that for a best response by the policymaker against a current mixed strategy by nature, it is necessary and sufficient that whenever the conditional expectation of yt given the sample strictly exceeds the conditional expectation of yt prime given the sample for two treatment possibilities t and t prime, then it must be the case that the best response gives 0 weight to the dominated treatment t prime. That's trivial by the law of iterated expectations. Okay, but given that we are calculating a best response against a known mixed strategy, okay, the policymaker knows what mu n is. Those objects here can be calculated explicitly as a function of mu n and the sample wn. They are given to us in closed form. So we can decide whether this is true or not true. So if this is true, then you assign 0 probability to t prime. Okay. So you can work out exactly what a optimal response is. If you have a tie here, by the way, then it doesn't matter which treatment you are assigning to. So you can either put weight 1 to treatment t or weight 1 to treatment t prime. So in other words, you can always find explicitly, trivially, a best response, okay, using that insight here. Okay, so here are the details. Okay, just showing you how to calculate that conditional expectation, but it's completely trivial. Okay, it's just exploiting the notion of a conditional distribution. Okay, so, and here we're also using that yt is binary. So the expected yt given wn is just the probability that yt is equal to 1. Then we use the law of total probability here, and then you just use base rule basically. Right, it's completely straightforward. So that's maybe the key insight of the first paper. Okay? The best response by the policymaker is given in closed form. I already mentioned the nice features of the algorithm that whoever implements that algorithm is always informed at every step of the algorithm how far the current treatment policy is at most away from the minimax regret value, because we always get an upper bound and a lower bound in every step of the iteration on the actual minimax regret value. Okay, so let me give you some results for this seemingly trivial setup here where we have two treatments to choose from. We take the unrestricted space of mean vectors in these simulations here, and we take 1,000 grid points when we do the discretization. So, okay, so rather than using the entire unit interval, you just take 0, 1 over 1,000, 2 over 1,000, and so on. We experiment with different weights. So these are the weights that Robinson suggested, and these are the ones that we found in our simulations do better than the Robinson ones. We experiment with different initializations. We take an empirical success rule and also something that is clearly suboptimal. It's just to determine how much the initialization actually matters for the performance of the algorithm. And we started with a balanced sample where we have equal number of observations for each treatment. That's one of the few instances where we have analytical rule. So that's very handy to assess whether our algorithm works well, because we know actually what the best performance looks like. So here, Steuer also gives us a formula for the minimax regret value in that setting, so it's equal to that number. So the following table reports the maximal regret of delta n, so the maximal regret of the treatment policy in the nth iteration for various number of iterations. So here in the first row, we report the maximal regret of the treatment policy used in the initialization step after 150 iterations, 500 and 2,000 iterations. Here we experiment with different weighting schemes, alpha n, okay, and different initializations. Okay, so columns are different combinations of initializations and weighting schemes. So what you see is that after 2,000 iterations, the treatment policy delta 2,000 has a maximal regret that gets very, very close to the actual minimax regret value, up to at least 3 digits, right? So, okay, what we also find is that the effect of the initialization disappears very quickly. So obviously here, this is a very suboptimal initialization, right? It has gigantic maximal regret. But if you look here, after 2,000 iterations, oftentimes actually starting off with the suboptimal initialization, you end up with a smaller maximal regret after 2,000 iterations than when you start with something that seems to be reasonable, empirical success rule, for example. And we also find that the weights that we suggest lead to quicker convergence. So if you compare this column with this column, we are getting a smaller maximal regret than we have here. Okay, so initialization is not so important. What is important is to pick a reasonable weighting scheme. In terms of computation time, to produce that table takes less than a minute here on my home computer using Julia. Previously with Gauss, it took about 1.5 hours. So it's a substantial improvements. We've considered sample size up to 1,000 just for comparison and to outline how powerful the insight is that we don't have to calculate by grid search, say the best response by the policymaker. If you look at previous papers that attempted computational approaches to calculation of or approximation of minimax regret rules, Mussen 2023 uses some sort of convex optimization, if I remember correctly. And the sample sizes that I handled in that paper are just single digits, like N1 is equal to 1 and N2 is equal to 3. So sample sizes that small, because that's how complicated a problem it is if you don't use that trick. Okay, so then we do unbalanced samples for which there's no analytical result. And again, we find that convergence is very, very quickly achieved. Okay, so in each case, after 2,000 iterations, the algorithm generates a treatment rule whose maximal regret is less than 10 to the minus 4, larger than the minimax regret value. So here we are reporting the difference between the upper bound and the lower bound. So this will go to 0, and here we can always see by how much at most the current treatment policy differs in terms of maximal regret from the minimax regret value. Okay, so after 2,000 iterations, you get something that I think you can be very happy with. Okay, and now we look at an example where we introduce include a priori knowledge. So M, instead of being 0, 1 to the 2, is now restricted. And such situations, as I mentioned previously, arise very frequently in practice. For example, expected wage after job training should be non-smaller. If you also factor in the job training cost C, then you end up with an inequality of that sort here. mu1 being smaller or equal to mu2 plus C. Okay, so here we do something similar. And what we find is, again, convergence works very well, right? So here we have the difference between upper and lower bound for different sample sizes. Here we have a number of iterations. In each case, we have convergence, right? The difference goes to 0 between upper and lower bound. And what we also find importantly is that the empirical success rule, which we use for initialization, can be very, very suboptimal when you have restrictions on the space of m vectors. So here, for example, after 2000 iterations, you get something, a treatment policy whose maximal regret is like 1/2 of the maximal regret of the empirical success rule. Okay, so I mentioned all that. Yeah, and I already mentioned that we can also include a binary covariate. And here also, including binary covariate, we document that there are substantial reductions in maximal regret of the rules obtained by the algorithm relative to what is called conditional on X or pooling in the literature. So when you have say a binary covariate, let's say male, female, then if you believe that treatment outcomes are very, very close on the different genders, then it makes sense to just pool the data. When you have to make a decision of what treatment to apply to males, you are incorporating the data from females. Because if you think that the outcomes are very, very close to each other, then the data from female is very informative also for males. So you would do what is called pooling. Okay, you would just pool all the data together. On the other hand, if you think that they could be substantially different, mean outcomes for women and mean outcomes for men, then you should do what is called conditional on X, that when you make a decision on men, you completely ignore the data from women. So Steuer 2009 has an analytical result that says that if the space of mean vectors is completely unrestricted, so you could potentially have mean outcome for women equal to 0 and mean outcome for men being equal to 1 for the same treatment, then you should do conditional on X. Okay, that is minimax regret optimal. And here's another result where he shows that pooling is minimax regret optimal if the means are known to be very close to each other. So, but here we show that in certain instances, okay, like for the space of m vectors that I just, the space of mean vectors that I just gave, the treatment policy that comes out of the algorithm after 2000 iterations substantially improves in terms of minimax regret value over conditional on X and pooling. Okay, that's one of the key results of the paper. Okay, so I think I'm basically done with time, right? So I'm giving you some options. So I can juxtapose our numerical approach to convex optimization and discuss what I believe are the advantages. So the algorithm in particular is called multiplicative weights that the Cornell lab introduced. I can talk about the coarsening approach, which I find is extremely interesting. So it's this result that says that attention can be restricted to binary outcomes, because once you have a minimax regret treatment rule for the binary case, then you can analytically generate a minimax regret treatment rule for that general space of potential outcomes. So it's a very cute result, unfortunately not due to us. We simply twist and modify it a little bit, but the main insights go back a long time. So, okay, so I'll talk about this. All right. So let's now assume that potential outcomes live on the unit interval. And I want to discuss the coarsening trick. How can we generate analytically a minimax regret rule if we have a minimax regret rule for the binary case? Okay, what you do is the following. Let's assume that this is the data set that you observe. Okay, so you have an individual one that was given treatment 1, and that's the outcome that was generated. That's now all those are numbers that live on the unit interval. So that could be 0.3, this could be 0.8, and so on, right? So the idea is to coarsen those outcomes, which means that you transform them to become zeros or 1. Okay, and then you simply apply the previous algorithm to that coarsened data set. So how do we coarsen? We are replacing each observation by an independent draw from a Bernoulli distribution with success probability equal to the observation. Okay, so for example, if this was a 0.3, then you use a Bernoulli distribution with success probability 0.3. You obtain A0 or A1, okay? And let's denote by the tilde notation the coarsened outcomes. And then, as I already said, we are simply denote by W and tilde the coarsened data set, and you simply apply to the coarsened data set the minimax regret treatment rule from the binary world. And that magically ends up to be minimax regret optimal for the more complex potential outcome distributions. Okay, and I have the proof. It's very simple actually. So I'll go through the proof and then we call it a day maybe. So one word about the rules that we are generating here. They are typically randomized rules, which may be for empirical practice, maybe a little off-putting. So for example, assume that you are going to your cardiologist and he's contemplating surgery and he says, we have that paper here that has a randomized treatment rule that is optimal. So let me now randomize whether we do that surgery or not with probability 0.3. We're going to decide whether or not we're going to do that surgery. You may find that slightly weird, right? But it turns out that this is...
You don't try to give 0.3 of a surgery of an actual surgery, so it's still...
Yeah, okay, so here's the proof. First, the proposition, which is writing down formally what I just said in Word. So it is minimax regret optimal for the more general outcome space here, 0, 1, the unit interval, to apply the minimax regret rule from the binary world to the coarsened outcome. So here, coarsened outcome, a coarsened data set, you apply the minimax regret rule from the binary world, and that turns out to be minimax regret optimal in the general outcome space. Okay, what is the idea? How does the proof work? It's just 2 pages, so very simple. Okay, first observation is that the unconditional distribution of YTII tilde is Bernoulli. Okay, obviously, right? Because we are generating zeros and 1. The insight here is that it has success probability mu ti, so equal to the original mean of ti. And why is that? It's simply an application of the law of iterated expectation. So one-line proof. So by the law of iterated expectation, the unconditional distribution of YTI tilde is Bernoulli this success probability. Therefore, the distribution of the coarsened sample depends on S, so the joint distribution of potential outcomes, again, only through the mean vectors. Why is that? Well, the sample is still generated in an IID fashion. So in particular, the observations are independent of each other. Therefore, instead of joint, only marginal distributions matter. And given that we have Bernoullis, again, everything is pinned down by the means, and the means are the original ones. So the distribution of the coarsened sample depends on the joint DGP only through the mean vector, the original mean vector. Denote by delta tilde the coarsened version of a particular treatment rule delta. Then, because you can always write regret like this, it follows that the regret of the coarsened treatment rule for given S depends on S only through the mean vector. Okay, so why is that? We have said that the coarsened sample depends on S only through the mean vector. And what else is here? Well, the coarsened sample, and otherwise we only have the mu's, right? Nothing else of S related to S appears here. So the regret of the coarsened sample for given S depends on S only through the mean vector, because the distribution of the coarsened sample depends on S only through the mean vector. So all very trivial steps. Okay, so now we're almost done. Denote by S prime the distribution obtained from an arbitrary S by replacing each marginal YT with a Bernoulli distribution with the same expectation. You can always do that, right? And denote by S prime the space of all such distributions S prime. So it's S prime contains certain Bernoulli distributions. And trivially, given that S is completely unrestricted, S prime is a subset of S. By construction or by definition of S prime, they have the same mean vector, and therefore, by the result that we just discussed, if we have the same mean vector under the coarsened treatment rule. It follows that the two regrets have to be the same, right? Given that S and S prime have the same mean vector, the resulting regrets for the coarsened rule have to be identical. That's exactly the result that we stated here. The regret for the coarsened rule for a given S depends only on the mean vector. So if you plug in here different S's with the same mean vector, you get the same regret. Okay, so this is this result. Then last observation, because under S prime is Bernoulli distribution, so it only generates data with zeros and one. So if you talk about coarsening such a data set, you're not changing anything because you already start off with zeros and ones. So under S prime, the coarsened sample is equal to the original sample because you already started off with 0 ones. Therefore, so coarsening doesn't change anything. Delta tilde is equal to delta. Therefore, we have R delta tilde S prime equal to R delta S prime, trivially. Now, putting those two guys together, you end up that this equality holds. Okay, so let's keep in mind that we have this equality here. Now we are really done. We just have to realize that we have that string of inequalities. So here we are taking the minimum over all treatment policies and we max over all the S prime, so a bunch of Bernoulli distributions. This is smaller equal to this quantity because here we are maxing over all S's and we have this inclusion here. So trivial. Also, this inequality is trivial because here we are minimizing only over the coarsened treatment policies, whereas here we are minimizing over all treatment policies. So we trivially also have this inequality. But given now that those two guys are the same, it follows that the inequalities are actually equalities. And therefore, you find that if delta is a minimizer in the Bernoulli world, so it's a regret minimizing treatment policy in the Bernoulli world, the coarsened version of delta is a regret minimizing treatment policy in the more complicated world where outcomes live on the unit interval. So very trivial proof, but so powerful. Okay, so we only have to worry about the binary world. Then you get everything through the coarsening trick in the more complicated setup. Okay, so, and I'm not gonna go into details with the pilot project. Luckily, I gave that overview at the very beginning of my talk. So, yeah. So just saying that the insights from the first paper can be used to overcome any hurdle that you come across in the pilot project. So we also have a coarsening approach there. And then conclusion, in a setup where potential outcomes YT live in the unit interval, we provide a two-step method that consists of a feasible algorithm that applies in the binary case. So feasible, at least if T is not too big, right? So maybe T equal to 2, 3, 4 maybe. And a coarsening approach to generate a sequence of treatment rules whose minimax regret, whose maximal regret, it should say, whose maximal regret converges to the minimax regret value of the discretized model. And importantly, that was the key step that made that project feasible, is that the policymaker's minimization problem is given in closed form and tackled by comparisons of conditional means. Okay, and then we document in the second project the flexibility and versatility of the algorithm by applying it to a rather complicated action space for the policymaker that includes design choice and treatment assignment in the end.